The average CL change is greater at the low AOA at the tip chords, while the amount of change of the CL is much less at higher AOA at the root chord. End of page 2 to 14. Therefore, an increase in AOA for the wing results in the tips creating a greater proportion of the lift and moving the center of lift behind the CG, creating a negative pitching moment to lower the nose at high AOA. Based on the same principle, when the wing AOA is lowered below the trim position, the tip chord CL decreases more than the root chord in the center of lift for the wing moves forward, creating a positive moment to raise the nose at lower AOA. In situations where the pilot is flying in severe/extreme turbulence, wind shear, or the pilot is exceeding the limitations of the aircraft, the WSC aircraft can get into a situation where the root chord is at a negative AOA and not producing lift. This could result in an emergency vertical dive situation, as discussed later in the whip stall tuck tumble section. When at very low angles or negative angles of attack, the WSC wing is designed so that the wing has positive stability or a nose-up aerodynamic moment. This is accomplished by a number of different systems: washout struts, sprogs and reflex lines, further explained in Chapter 3, that simply keep the trailing edge of the wing up in an emergency low/negative AOA dive situation. As shown in Figure 2.29, the root area of the wing has reflex, which creates a positive pitching moment for the root chord to rotate the nose up towards a level flying attitude. At the same time, the tips are at a negative AOA, producing lift in the opposite direction as usual, creating a moment to bring the nose/root chord up to a positive AOA to start producing lift and raising the nose to a normal flight condition. The negative lift or downward force as produced at the tips and root is shown provide a positive moment to raise the nose back to a normal flying attitude. End of page 2 to 15. Reflex also provides a stable pitch-up moment for an airfoil when it is flying at normal flight angles of attack. The greater the reflex, the greater the nose-up moment of the airfoil. This is used in some WSC airfoil designs and also for trim control, as discussed in Chapter 3. Carriage moments. The wing design is the main contributing factor for pitch stability in moments, but the carriage design can also influence the pitching moment of the WSC aircraft. For example, at very high speeds in a dive, a streamlined carriage would have less drag and, therefore, a greater nose-up moment because of less drag. The design of the carriage parts can have an effect on aerodynamic forces on the carriage, resulting in different moments for different carriage designs. The drag of the wing in combination with the drag of the carriage at various airspeeds provides a number of pitching moments, which are tested by the manufacturer, a reason the carriage is matched to the wing for compatibility. Each manufacturer designs the carriage to match the wing and takes into account these unique factors. Pitch moments summary. Overall, the amount of sweep, twist, specific airfoil design from root to the tip, and the carriage design determine the pitching moments of the WSC aircraft. Some have small pitching moments, some have greater pitching moments. Each WSC model is different, with a balance of these aerodynamic parameters to accomplish the specific mission for each unique carriage and wing combination. Roll stability and moments. As described in the Pilot's Handbook of Aeronautical Knowledge, more dihedral or less anhedral in a WSC wing creates more roll stability. More roll stability might be helpful for a training wing or a fast wing made for long cross-country straight flight, but most pilots want a balance between roll stability and the ability to make quicker turns and a sport car feel for banking/turning. Therefore, a balance between the stability and the instability is achieved through anhedral plus other important wing design features such as nose angle, twist, and airfoil shape from root to tip. An aerodynamic characteristic of swept wings is an effective dihedral based on the sweep of the wing and angle of attack. The combination of the physical anhedral in the wing and the effective dihedral due to wing sweep provides the balance of stability and rolling moments for a particular wing design. The design of the wing can have actual dihedral or anhedral in the wing. Even with anhedral designed in the inboard section of the wing, the outboard sections of the wing could have some dihedral because of the flex in the outboard leading edges. As the wing is loaded up from additional weight or during a turn, the tips flex up more, creating more dihedral and a roll stabilizing effect when loaded. Figure 2.30. Generally, it is thought that the wing remains level and the weight shifts to the side to initiate a turn. Another way to look at how the WSC wing rolls is to examine the carriage and the wing moment from the carriage point of view. For example, the CG hangs far below a wing weighing 1/8 of the carriage weight. When the control bar is moved to the side, creating a moment about the carriage/wing hang point, the carriage stays vertical and the wing rotates around the carriage. Therefore, there are two rolling moments that both contribute to the WSC rolling into a bank. 1. The pilot creating the force on the control bar rotating the wing about the wing/carriage hang point. 2. Shifting weight to one side of the wing, thus warping the wing to aerodynamically change the lift on each side, as in airplane roll control. Figure 2.31. End of page 2 to 16. Carriage moments. Carriage weight and resultant CG are the main factors that contribute toward increasing the roll moment for the carriage. Carriage aerodynamic forces are not typically a factor for rolling moments. Roll stability summary. Overall, roll stability and moments are a manufacturer/make/model balance between dihedral/anhedral, wing twist, nose angle, airfoil shape from root to tip, and leading edge stiffness. Some designs are stable, others neutral, and others can be designed to be slightly unstable for quick side-to-side rolling. Yaw stability and moments. There is no significant turning about the vertical axis because the WSC wing is designed to fly directly into the relative wind. Any sideways skidding or yaw is automatically corrected to fly straight with the swept wing design. An airplane uses the vertical tail to stabilize it to fly directly into the relative wind like a dart. The unique design of the WSC aircraft performs the same function through the swept wing design, but also the wing twist and airfoil shape from root to tip assists in the correction about the vertical axis. A simple way to understand the yaw stability is to see that any yawing motion is reduced simply through the increased area of the wing as it rotates about its vertical axis. Figure 2.32. There is a slight amount of adverse yaw similar to an airplane that can be noticed when a roll is first initiated. The amount varies with the specific manufacturer's design and make/model. In addition, the wing can yaw side to side to some degree, with some different manufacturers make/model more than others. The higher performance wings with less twist and a greater nose angle are noted for less yaw stability to gain performance. These wings also require more pilot input and skill to minimize yaw instability through pitch input. In addition to the wing platform, twist, and airfoil shapes to minimize yaw, some wings utilize vertical stabilizers similar to these in airplanes and others use tip/NS. Figure 2.33. Generally, the WSC wing is yaw stable with minor variations that are different for each wing and can be controlled by pilot input, if needed. Carriage moments. The wing is a significant factor in the design of yaw stability, but the carriage can be a large factor also. If the area in front of the CG is greater than the area in back of the CG, and the wing yaws to the side, then the front would have more drag and create a moment to yaw the WSC aircraft further from the straight flight. End of page 2 to 17. Therefore, FAA-NS are sometimes put on the carriage as needed so the carriage also has a yawing aerodynamic force to track the WSC aircraft directly into the wind. Figure 2.34. Since the carriage has such a large effect on yaw stability, the carriage is matched to the wing for overall compatibility. Each manufacturer designs the carriage to match the wing and takes into account these unique factors of each design. Yaw stability summary. These factors make the WSC aircraft track directly into the relative wind and eliminate the need for a rudder to make coordinated turns. Designs and methods vary with manufacturer and wing type, but all WSC wings are designed to track directly into the relative wind. Thrust moments. WSC aircraft designs can have different moments caused by thrust based on where the thrust line is compared to the CG. This is similar to an airplane except the WSC aircraft has no horizontal stabilizer that is affected by propeller blast. If the propeller thrust is below the CG, figure 2.35, top, this creates a pitch-up moment about the CG when thrust is applied and a resultant decrease in speed. When reducing the throttle, it reduces this moment and a nose pitch down results with an increase in speed. If the propeller thrust is above the CG, figure 2.35, bottom, this creates a pitch down moment about the CG when thrust is applied and a resultant increase in speed. When reducing the throttle, it reduces this moment and in nose pitch-up results with a decrease in speed. With the thrust line above or below the CG producing these minor pitch and speed changes, they are usually minor for most popular designs. Larger thrust moments about the CG may require pilot input to minimize the pitch and speed effects. Most manufacturers strive to keep the thrust as close as possible to the vertical CG while also balancing the drag of the carriage and the wing for its speed range. This is why the carriage must be matched to the wing, so these characteristics provide a safe and easy to fly WSC aircraft. Stalls exceeding the critical AOA. As the AOA increases to large values on the wing chord, the air separates starting at the back of the airfoil. As the AOA increases, the separated air moves forward towards the leading edge. The critical AOA is the point at which the wing is totally stalled, producing no lift regardless of airspeed, flight attitude, or weight. Figure 2.36. End of page 2-18. Because the AOA of the WSC wing root chord/nose is so much higher than the AOA of the tips, the nose stalls before the tips. It is similar to stalling with the airplane canard, in which the nose stalls first, the main wing, or tips for the WSC aircraft, continues to fly, and the nose drops due to lack of lift. In most normal situations, the root chord/nose stalls first because it is at a much higher AOA. The tips continue to fly, making the WSC wing resistant to a complete wing stall. A pilot can even bring the aircraft into a high pitch angle stall attitude and keep the nose high. The nose stalls and rotates down because of the loss of lift, while the tips keep flying and maintain control of the aircraft. If flying within the operating limitations of the aircraft and the WSC reaches a high AOA, the nose stalls, but the tips continue flying. However, it must be understood that there are many wing designs with many types of stall characteristics for each unique design. For example, high-performance wings could have less twist to gain performance, which could cause the wing to stall more abruptly than a training wing with more twist. Whip stall, a tuck, a tumble. A WSC aircraft can get to a high pitch attitude by flying outside its limitations or flying in extreme/severe turbulence. If the wing gets to such a high pitch attitude and the AOA is high enough that the tips stall, a whip stall occurs. Figure 2.37. In a WSC wing, most of the area of the wing is behind the CG, about 3/4. With the tips and aft part of the wing having the greatest drag, and the weight being forward, an immediate and strong nose-down moment is created and the WSC nose starts to drop. Since both the relative wind and the wing are rapidly changing direction, there is no opportunity to re-establish laminar airflow across the wing. End of page 2-19. This rotational momentum can pull the nose down into a number of increasingly worse situations, depending on the severity of the whip stall. Figure 2.37 shows a whip stall and the phases that can result, depending on the severity. Phase 1, a minor whip stall, results in a nose-down pitch attitude at which the nose is at a positive AOA and the positive stability raises the nose to normal flight, as described in Figure 2.25c. Phase 2, if the rotational movement is enough to produce a vertical dive, as illustrated in Figure 2.29, the aerodynamic dive recovery might raise the nose to an attitude to recover from the dive and resume normal flight condition. Phase 3, the rotational momentum is enough to bring the nose significantly past vertical, the nose is tucked under vertical, but could still recover to a vertical dive and eventually resume a normal flight condition. Phase 4, the rotational momentum is severe enough to continue rotation, bringing the WSC wing into a tumble from which there is no recovery to normal flight, and structural damage is probable. Avoidance and emergency procedures are covered in Chapter 6, Basic Flight Maneuvers, and Chapter 13, Abnormal and Emergency Procedures. Weight, load, and speed. Similar to airplanes, sailplanes, and PPCs, increasing weight creates increases in speed and descent rate. However, the WSC aircraft has a unique characteristic. Adding weight to a WSC aircraft creates more twist in the wing because the outboard leading edges flex more. With less lift at the tips, a nose-up effect is created and the trim speed lowers. Therefore, adding weight can increase speed similar to other aircraft, but reduce the trim speed because of the increased twist unique to the WSC aircraft. Each manufacturer's make/model has different effects depending on the specific design. As described in the Pilot's Handbook of Aeronautical Knowledge, the stall speed increases as the weight or loading increases, so some manufacturers may have specific carriage/wing hangpoint locations for different weights. Some require CG locations to be forward for greater weights, so the trim speed is well above the stall speed for the wing. WSC aircraft have the same forces as airplanes during normal coordinated turns. Greater bank angles result in greater resultant loads. The flight operating strength of an aircraft is presented on a graph whose horizontal scale is based on load factor. The diagram is called a VG diagram, velocity versus G loads or load factor. Each aircraft has its own VG diagram, which is valid at a certain weight and altitude. See the Pilot's Handbook of Aeronautical Knowledge for more details on the VG diagram. Load factors are also similar to the VG diagram applicable to WSC. Basic propeller principles. The WSC aircraft propeller principles are similar to those found in the Pilot's Handbook of Aeronautical Knowledge, except there is no corkscrewing effect of the slipstream and there is less P-factor because the carriage is generally flying with the thrust line parallel to the relative wind. The wing acts independently, raising and lowering the AOA in speed. This was introduced at the beginning of this chapter when angle of incidence was defined. The torque reaction does have a noticeable effect on the WSC aircraft. With the typical left-hand turn tendency, for right-hand turning propellers, turns are not typically built into the wing. As in airplanes, some cart designs point the engine down and to the right. Others do not make any adjustment, and the pilot accounts for the turning effect through pilot input. It should be noted that many of the two-stroke propellers turn to the right, as do conventional airplanes. However, many four-stroke engine propellers turn to the left, creating a right-hand turn. Consult the POH for the torque characteristics of your specific aircraft. Chapter Summary. Basic principles of aerodynamics apply to all aircraft. However, the unique design of the wing and the separate fuselage/carriage provide a simplistic and efficient aircraft. The following provide a summary of the unique aerodynamics for the WSC wing. 1. The WSC wing is pitch stable without a tail because of the combination of airfoil design from root to tip, sweep, twist, and planform. 2. WSC wing flexibility allows the wing to twist from side to side by shifting the weight, providing the control to roll the aircraft without control surfaces. 3. The WSC wing only has two axes of control, pitch and roll, while no yaw control is needed because it is yaw stable. 4. The WSC wing is stall resistant because under normal flight conditions the tip cord is still flying while the rest of the wing is stalled, similar to the airplane canard system. End of page 2 to 20. End of chapter 2. Please like, share, and subscribe to our channel. Chapter 3 is coming soon.